Welcome back to my YouTube channel. Today we'll be going over outliers, what they are, how to spot them, and what to do with them once we've spotted them. As usual, we'll be using the Palmer Penguins dataset. One more package which you may not have is called CalPlot, which is basically just a package that will allow you to easily combine graphs together into a single visualization. So if you don't have that, do go ahead and install it before you use the library function on it. Now, before we actually get into this proper, I want to go over some basic data distributions and just talk a little bit about what outliers are. Now, a classic way to look at and talk about outliers is by using a normal distribution. So if we look down here, basically what I've done with this little code snippet here is I've created this visualization of a normally distributed data set, or you might have heard it called a bell curve, and the defining characteristic of a normally distributed data set is a mean with which on either side the data basically forms a slow gradual decrease, or it basically ends up looking like a bell, or sometimes you might see a U shape assigned to it. And basically the defining characteristic is that data on either side of the mean is more or less equally distributed, and in the middle at the mean is where most of the data will be. So again, at the mean of 0, we have most of our the highest frequency of data. When standard deviation away from the mean, we have a bit less frequency. 2, we have less. 3, we have less, so on and so forth. And now to get at the question of outliers is, well, obviously, an outlier is what? An outlier is an observation within a variable or a data set that you think, hey, this shouldn't belong. It's too dissimilar to the rest of the data. Well, obviously the mean isn't going to be an outlier. It's not too dissimilar. What about one standard deviation away? There's still a lot of observations here, so probably not. What about 2? There's about 50 observations out of 1,000, so maybe not. 3, there's far fewer. 3, we're looking at maybe 10 observations. And in fact, 3 standard deviations away from the mean is actually a very common stop point to say, hey, anything more than this is an outlier and I will remove it. You may also sometimes run into the 2 standard deviation rule, which will say that basically anything that is 2 standard deviations or more away from the mean is to be considered an outlier and removed. The 2 standard deviation rule is also sometimes called the truncated mean rule. From what I remember, this is much more seen in the social sciences, where there is a lot of noise and a lot of variability around data. The more you'll go towards things like biology, chemistry, the more you'll be looking at 3 standard deviations, or sometimes maybe even more. And a popular way to detect and subsequently remove outliers is with a method called, using z-scores. And basically all z-scores are a way to rank your data based on how far it is away from your mean, and then you standardize it by your standard deviation. And so that's what I'm doing here with the code I just pasted in. Before we get into this, we'll just take our penguins data set and drop all of the missing values, because applying these kind of transformations, they don't handle missing values too well. And so just to get around that little headache, I'll do that before we get started. And so what we're going to do is we're actually going to create a value called z-scores, not a data frame, which is calculated sort of as I alluded to before, by taking the mean, or taking each value and then subtracting the mean from it. So in this case, we're using body mass, and we will subtract the mean from it. This will give us an absolute measure of how far away it is from the mean, and then we will standardize it by dividing it by the standard deviation. And all the standard deviation is basically a way to tell us the average distance between each data point, effectively. And so if we go, if we go ahead and we run this, we'll get all of these z-scores, 333 z-scores, some of which will be negative, some of which will be positive, obviously, because we haven't gotten the absolute measures for these yet, which is what we're going to do next. We're going to create another value called outliers, where we will take the absolute value of all the z-scores, and then we will say that, hey, anything that is above 1.5 z-scores, so 1.5 standard deviations in this case, because z-scores and standard deviations are analogous, will be considered an outlier. Now, if you'll remember to maybe a minute and a half to 2 minutes in the past, I said usually you'll want 2 or 3 standard deviations away from your mean to be considered an outlier. However, the Penguins dataset doesn't really have outliers, so just for the sake of an example, I'll use 1.5 so that I can illustrate my point and I can show you, or we can visualize a data frame that has been cleaned of quote-unquote outliers and a normal data set. So I'll go ahead and run this. And then basically to create a new data set, Penguins clean, I'll just take the Penguins data set and then I will remove the outlier values from it. It's a very simple transformation. And now if we look up here at our data, we see that we have roughly 40 or so data points that have been removed, quote unquote cleaned, but not really because these aren't really outliers. And now what we can do is I'll just copy this code that I made, and what we can do is we can visualize each of these data sets so that we can compare them side by side to see what they look like cleaned and uncleaned. So if I go ahead and run this, this may take a little bit of a time to load, if I remember correctly. All right, there we go. It finally loaded. And so what we have here on the left basically is the original data set. And what we have on, did I say the right? I meant the left. What we have on the left is the original data set. And what we have on the right is the clean data. And so if we look at the x-axis, which is the body mass, so let's look at the 6,000 grams and above. We clearly have some data here, but here we have nothing around 6,000. We have something maybe around 5,500, and the same thing around 3,000. There's nothing really below 3,000 grams, whereas here there's definitely some data that is below 3,000 grams, and that's exactly what you would expect from a data set that has had its outliers removed, because that's what you do. You remove the values that will be at the extreme of your data, either at the extreme left or the extreme right, the extreme lows and the extreme highs away from the mean. So I hope that was clear. Now, some among you might be thinking, well, what if my data isn't normally distributed? What if my data is skewed to the right or skewed to the left? So in this case, because we are standardizing it beforehand, it won't really have an impact if your data is not normally distributed, or not, or if your data is non-parametric. Another use case, or another case where this may not be useful, might be with time series data. So if you're looking at, let's say, stock prices over 2-3 years, obviously the stock prices will probably not remain in the same range. So if you just use a single mean to then judge all of your data on, you're going to basically delete most of your data. And that's why in the next video, we'll be looking at a way to deal with data that is what's called a multinomial, that has more than one mean, basically, as most real world data does. So for example, just as a quick ahead for the next video, if you're looking at stock data that is fluctuating over time and you just use a single mean, as I've said, you'll end up deleting most of it, because you might start at a stock price of $20 and end up with 300, and your mean might be like 50. So anything that's like $10 to like $75 will be considered normal, and everything outside of that will get deleted, which will make absolutely no sense. However, if you use something like a rolling mean, so every 5 or 10 or 20 or 30 observations, you get a mean, and then you say, hey, based on this mean, all of the data sets within this sample of 30, what's an outlier? And then you do that for every bin of 10 or 30 or 50 or whatever. And so it makes cleaning up time series data make a lot more sense. And so in the next video, we'll be looking at how to do that specifically with a technique called Windsorization, which will actually not delete any values. It will actually transform your values. So you're not losing anything in your data set. So yeah, I hope that made sense. As I've said, in the next video, we'll be looking at Windsorizing data with a rolling mean. And after that, we'll be going over more basic data cleaning tips. And once my series of 7 or 8 videos on basic data cleaning is done, I'll then be releasing a 40 to 50 minute video that will be an end-to-end data cleaning project, which you'll be able to use as a portfolio project, because that time we won't be using Palmer penguins. We'll be using a real data set, and we'll be dealing with real data problems, not fabricated data problems as I've made it up here. Yeah, that's it. I hope you enjoyed the video. I still have no outro, so have a good day.